Welcome! In this session, we'll tackle LeetCode problem number 510, Inorder Successor in BST2. This problem involves finding the Inorder successor of a specified node in a binary search tree, BST. We'll walk through the problem, explore the solution, and break it down step by step. Let's get started. The problem is to find the Inorder successor of a given node in a binary search tree, or BST. The Inorder successor of a node P is defined as the node with the smallest key that is greater than P.val. Each node in the tree is represented using a node class, which includes attributes for the value of the node, its left and right children, as well as a parent pointer. This parent pointer allows the algorithm to traverse upward in the tree, even though we are not given access to the root of the tree. Instead, the input consists of only the node P4, which we need to determine the Inorder successor. In this problem, you can assume that the given node P will always exist in the tree. The function Inorder Successor takes a single argument, the node P, and returns the successor node. Let's consider an example to understand this better. Imagine a tree with 3 nodes. The root has a value of 2, with a left child of 1 and a right child of 3. If the input node P has a value of 1, we need to determine which node is its Inorder successor. The output for this example would be the node with value 2. Looking at the Inorder traversal of the tree, which visits nodes in ascending order, the sequence is 1, 2, 3. The successor of the node with value 1 is the next value in this sequence, which is 2. Now consider a second example with a larger tree where the root is 5, the left subtree contains nodes 3, 2, 1, and 4, and the right subtree has a single node 6. If the input node P has a value of 6, we need to determine its Inorder successor. In this case, the output is null. The Inorder traversal of the tree is 1, 2, 3, 4, 5, 6, and since the node with value 6 is the largest in the tree, it does not have any successor. Therefore, the result is null. Now, let's look at another example with a different tree structure. The root is 15, with a left child of 10 and a right subtree containing nodes 20 and 17, where 17 is the left child of 20. If the input node P has a value of 15, we need to identify its Inorder successor. The output for this example is the node with value 17. The Inorder traversal of this tree results in the sequence 10, 15, 17, 20. The successor of the node with value 15 is the next node in this sequence, which is 17. To summarize, the constraints of the problem include up to 10,000 nodes in the tree, with unique node values ranging from -100,000 to 100,000. Key edge cases to consider include nodes with right children, nodes without right children, and the largest node in the tree, which does not have an Inorder successor. To solve the problem of finding the Inorder successor of a given node in a binary search tree, we explored several approaches, starting with the brute force method. The intuition behind this approach is to perform an Inorder traversal of the tree, which naturally gives us the nodes in sorted order. Once we have the complete traversal stored in a list, we can locate the given node and simply return the next node in the sequence. While straightforward, this method has significant drawbacks. Both the time complexity, which is O(n), due to traversing the entire tree, and the space complexity, also O(n), for storing all nodes, make this inefficient. Additionally, this approach does more work than necessary, as we only need the successor of a single node, not the entire ordered list of nodes. Next, we considered an optimized approach that takes advantage of the properties of a binary search tree. The key observation here is that the Inorder successor of a node can be determined without traversing the entire tree. If the node has a right child, the successor is the leftmost node in its right subtree. On the other hand, if the node has no right child, we need to look upward in the tree to find the lowest ancestor for which the node is part of its left subtree. This can be done efficiently using the parent pointer provided in the problem. The time complexity of this approach is O(h), where h is the height of the tree, which means it's O log n, for a balanced BST. The space complexity is O(1), since no additional space is required. However, this method requires careful handling of edge cases, such as when the given node is the largest in the tree or when the tree is unbalanced, making it skewed. The optimized approach was chosen as the best solution due to its efficiency and direct utilization of BST properties. Unlike the brute force method, it avoids the overhead of traversing the entire tree and storing all nodes, making it much more suitable for larger trees. The parent pointer provided in this problem is especially useful, as it allows us to traverse upward in the tree without recursion or additional data structures. A key insight here is that the inorder successor can always be determined by either moving to the right subtree or traversing upward to the lowest ancestor that satisfies the conditions. Between the brute force and optimized approaches, the trade-offs are clear. While the brute force method is simpler to implement, it is inefficient in terms of time and space. Additionally, we chose an iterative implementation of the optimized approach to further reduce space complexity, avoiding the O-H space used by recursion. The final strategy we implemented relies on the optimized approach using the BST properties and the parent pointer. This method achieves the desired result with minimal time and space complexity, making it highly efficient. It also effectively handles all edge cases, including scenarios where the node has no right child or is the largest in the tree. By leveraging the parent pointer, we simplified the traversal process, ensuring the solution is both space-efficient and robust. This approach strikes the right balance between complexity and performance, making it the ideal choice for solving this problem. The problem we are tackling here is LeetCode number 510, where the goal is to find the inorder successor of a given node in a binary search tree. Remember, the inorder successor of a node is the node with the smallest key greater than the current node's key. What makes this problem unique is that each node not only has left and right pointers but also includes a reference to its parent. This additional parent pointer is crucial for our optimized approach. To solve this, we begin by understanding two main scenarios. First, if the node has a right child, the inorder successor will always be the leftmost node in the right subtree. Second, if the node has no right child, the successor will be one of its ancestors. Specifically, it is the lowest ancestor for which the input node lies in the left subtree. Let's break this into steps. For the first case, when the node has a right child, we start by moving to the node's right child. From there, we traverse downward through the left subtree until we find the leftmost node. This leftmost node will be the inorder successor. This approach ensures that we identify the smallest node in the right subtree efficiently. Now, for the second scenario where the node does not have a right child, we need to rely on the parent pointer. Starting from the given node, we move upward through its ancestors. We continue this process until we find a node that is the left child of its parent. The parent of this node will then be our inorder successor. If no such ancestor exists, this means the input node is the largest node in the BST, and in this case, the function should return null. Why do we need these two distinct cases? This is because of the nature of an inorder traversal in a BST. When a node has a right child, its successor must naturally lie within the right subtree. In contrast, when there is no right child, the successor is found higher up in the tree among the ancestors. The parent pointer plays a critical role here, allowing us to traverse upwards in the tree without any additional data structures. This eliminates the need for recursion or an external stack, making the solution space-efficient with an O(1) space complexity. Finally, the time complexity is determined by the height of the tree, which means it is O(h). For a balanced BST, this further reduces to O log n. In terms of implementation, the node structure is quite important. Each node in the tree contains val, left, right, and a parent pointer. The parent pointer is what allows us to traverse upward efficiently. Without it, we would need to maintain a stack or use recursion, both of which would increase the space usage of our solution. Let's also consider a few edge cases to ensure the algorithm handles all scenarios. First, if the input node is the largest node in the tree, it will have no right subtree and no valid ancestor, so the function should return null. Second, if the node has a right child but no left descendant in that right subtree, the right child itself will be the successor. Lastly, in a degenerate tree, which is essentially a linked list with all nodes having only left or only right children, the algorithm still works seamlessly since it simply traverses up or down as needed. The pseudocode for the solution demonstrates the simplicity of this approach. We first check for the right child scenario. If there is a right child, we traverse to the leftmost node in the right subtree and return it. Otherwise, we move upward through the parent pointers to identify the correct ancestor. The actual implementation in Python is straightforward and follows the pseudocode. If the input node has a right child, we move to that child and then iterate down its left subtree until we reach the leftmost node. This node is returned as the successor. If the input node does not have a right child, we use the parent pointer to traverse upward. We continue moving up until the current node is the left child of its parent. At this point, the parent becomes the inorder successor. If no such parent exists, we return null. To see this in action, consider the following example tree. The root node is 5, with left and right children 3 and 6, respectively. Node 3 further has 2 children, 2 and 4, and node 2 has a single left child, 1. This structure will help us understand how the algorithm navigates the tree to find the inorder successor in various scenarios. Let's go through a few examples using this tree. First, consider node 4. Since it has no right child, we move upward. Starting at 4, we go to its parent, node 3, but note that 4 is the right child of 3, so we continue upward to node 5. Here, 3 is the left child of 5, so 5 becomes the inorder successor of 4. Next, take node 3. This node has a right child, so we move to the right child, node 4. Since node 4 has no left child, it is the inorder successor of 3. Finally, consider node 6. Node 6 has no right child and no ancestors where it is a left child, meaning it is the largest node in the tree. In this case, the function correctly returns null, as there is no inorder successor. These examples highlight how the algorithm adapts to different scenarios while maintaining efficiency and correctness. This solution determines the inorder successor of a given node in a binary search tree, BST, where each node has a reference to its parent. The algorithm handles 2 primary cases to find the successor. 1. Case 1, node has a right child. If the node has a right child, the successor is the leftmost node in the right subtree. This is achieved by traversing the left children of the right subtree until no more left children exist. The while loop ensures that we find the leftmost descendant in the right subtree, which is the inorder successor. 2. Case 2, node does not have a right child. When the node lacks a right child, the successor must be an ancestor. We traverse upwards using the node's parent reference until we find a node that is a left child of its parent. The parent of this node is the successor because, in inorder traversal, the parent would appear immediately after the current node. The algorithm efficiently determines the inorder successor by leveraging the properties of the BST and the parent pointers. The solution handles edge cases, such as when the node is the rightmost node in the tree, where no successor exists, and the function returns none. The time complexity is O(h), where h is the height of the tree, as we either traverse down the right subtree or traverse upwards to find the successor. Here, we define the structure of the node class, which represents each node in the binary search tree. It contains the value of the node, pointers to its left and right children, and a reference to its parent node. The constructor initializes these fields, setting the left, right, and parent references to null by default. Moving to the solution class, we implement the Inorder Successor method. The goal of this method is to find the inorder successor of a given node. The first case we handle is when the node has a right child. In such a scenario, the successor is the leftmost node in the right subtree. To find this, we initialize a pointer to the right child and iterate leftward until we reach a node with no left child. This node is returned as the successor. Now, for the second case where the node does not have a right child, we need to traverse upwards using the parent reference. Starting from the given node, we move up the tree until we find a node that is the left child of its parent. This means the parent of the current node is the inorder successor. If we reach the root without finding such a parent, the given node has no successor, and we would return null. This approach leverages the parent references efficiently to determine the successor in scenarios where there is no right subtree, ensuring the solution handles all possible cases. To solve this problem, let's consider the first example where the given node has a right child. The input binary search tree has the root node 3, with children 1 and 5, and node 5 has an additional child, 7. The target node here is 3. Since node 3 has a right child, which is node 5, the algorithm directs us to find the leftmost node in the subtree rooted at node 5. Starting at node 5, we check if it has a left child. It does not, so node 5 itself is the inorder successor of node 3. This is because, in an inorder traversal, the next node after 3 would be the smallest node in its right subtree, which in this case is node 5. Here, the final output confirms that the Inorder successor of node 3 is node 5. Now, let's move to a case where the given node does not have a right child. In this example, the input tree has the root node 6 with children 3 and 8, and node 3 has a left child, 1. The target node is 3. Since node 3 does not have a right child, we cannot look into its right subtree. Instead, we follow the parent references to move up the tree. Node 3 is the left child of its parent, which is node 6. According to the algorithm, when a node is the left child of its parent, the parent is the Inorder successor. Therefore, node 6 becomes the Inorder successor of node 3. The state changes and variables confirm this process. Starting at node 3, the current node is updated to its parent, node 6. The successor is then identified as node 6. Thus, the final output is that the Inorder successor of node 3 is node 6. Now, let's explore another scenario where the given node has no right child but is the right child of its parent. In this case, the input tree has the root node 6 with children 3 and 8, and node 3 has a right child, 4. The target node is 4. Since node 4 has no right child, we again traverse up the tree using the parent references. When moving up, we note that node 4 is the right child of its parent, node 3. In such cases, we must continue going up the tree until we encounter a node that is the left child of its parent. From node 4, we move to node 3, and here we see that node 3 is the left child of node 6. This makes node 6 the Inorder successor of node 4. The state changes reflect this traversal. The current node moves from 4 to 3, and finally to 6. As a result, the successor is identified as node 6. Therefore, the final output is that the Inorder successor of node 4 is node 6. The time complexity of solving this problem depends on two main scenarios. First, if the given node has a right child, the algorithm follows the leftmost path in the right subtree to locate the Inorder successor. In the worst case, this means traversing all the nodes along the height of the right subtree. For a balanced binary search tree, BST, the height is proportional to O log n, while in a completely skewed tree, the height can go up to O n. Therefore, the time complexity for this case is O h, where h represents the height of the tree. Second, if the node does not have a right child, the algorithm moves upwards through the parent pointers until it identifies an ancestor where the given node lies in the left subtree. This traversal is also limited to the height of the tree, leading to a time complexity of O h for this case as well. Combining these, the overall time complexity of the solution is determined by the tree's height, resulting in O h. The space complexity of this algorithm is O1, because it operates iteratively without relying on recursion or allocating any extra data structures. The memory used is limited to a few variables for tracking the current node and the potential successor during the traversal. Since no additional space is required, the algorithm is very efficient in terms of memory use. Now, let's look at the best, average, and worst-case scenarios. In the best case, the given node is the root, and its successor is either the immediate right child or the parent, which results in a time complexity of O1. In the average case, assuming a balanced BST, the height of the tree is O log n, leading to a time complexity of O log n. However, in the worst case, for a completely skewed tree resembling a linked list, the height is O n, making the time complexity O n. When compared to a naive approach, the current solution is significantly more efficient. A naive method might involve performing a full Inorder traversal of the BST, storing the results in a list, and then scanning the list to find the Inorder successor. This approach has a time complexity of O n for the traversal and an additional space complexity of O n for storing the traversal result. In contrast, the optimized solution leverages the parent pointers and the BST structure to limit the traversal to a maximum of O h, while using no extra space, making it both time and space efficient. Mathematically, the time complexity is proportional to the height of the tree, h. In a balanced BST, h is O log n, while in a skewed tree, h is O n. The algorithm's efficiency comes from the fact that it only traverses a single path in the tree, either downwards or upwards, keeping the traversal proportional to the height. With no recursion or auxiliary data structures used, the space complexity remains constant at O1. This makes the solution optimal with an overall time complexity of O h and space complexity of O1. When solving problem number 510, one of the most common mistakes is neglecting the parent pointer provided in the problem. This pointer is a key feature that simplifies the search for the Inorder successor, yet some solutions ignore it entirely and treat the tree as if it were a regular binary search tree. This oversight leads to unnecessarily complex solutions that traverse the tree from the root, resulting in higher time complexity. Another frequent issue is confusing the Inorder successor with the predecessor. Remember, the successor is the smallest node larger than the current node, not the largest node smaller. Misunderstanding this can lead to completely incorrect outputs. Additionally, it's easy to overlook cases where a node is a leaf without a right child. In such scenarios, the successor must be located by traversing upward through the parent pointer to find an ancestor where the node lies in the left subtree. Failing to account for this situation results in incomplete solutions that only handle nodes with right subtrees. Edge cases are another critical aspect to consider. For instance, what happens when the given node is the rightmost node in the binary search tree? In this case, no successor exists, and your solution should handle it gracefully without causing errors. Similarly, if the tree is empty, your solution must avoid runtime errors by accounting for this scenario. Another inefficiency arises when solutions traverse the entire tree unnecessarily, ignoring the advantages of the parent pointer and the properties of a binary search tree. This can lead to a time complexity of O(n) instead of the more optimal O(h), where h represents the height of the tree. Ensuring your approach is both efficient and robust is crucial to solving this problem effectively. To gain an edge during interviews, it's important to understand the two key cases for finding the Inorder successor. First, if the node has a right child, the successor is the leftmost node in the right subtree. Second, if there's no right child, the successor is the lowest ancestor where the node lies in the left subtree. These observations are foundational for this problem. To deepen your understanding, also practice finding the Inorder predecessor, as it builds on similar traversal concepts. The parent pointer is a particularly valuable tool for optimizing upward traversal in the tree. Furthermore, during interviews, it's essential to clearly articulate the difference between the two cases, right child versus no right child. This demonstrates a structured and methodical approach to problem solving, which is highly valued. This problem is closely related to several others that you may also encounter. For example, problem number 285, Inorder successor in BST, involves a similar task but without the parent pointer, requiring you to start from the root node. Problem number 173, binary search tree iterator, focuses on simulating an Inorder traversal using an iterative approach with a stack. Another related problem is number 426, convert binary search tree to sorted doubly linked list, where the goal is to preserve the Inorder relationship while transforming the tree. Finally, problem number 701, insert into a binary search tree, emphasizes understanding BST insertion, which is foundational for problems involving successors and predecessors. Familiarity with these problems will strengthen your grasp of BST concepts and prepare you for variations in interviews. There are multiple approaches you can take to solve this problem, each with its own trade-offs. The recursive approach is simple and intuitive. If the node has a right child, recursively find the leftmost node in the right subtree. Otherwise, traverse upward using the parent pointer. However, this approach risks stack overflow for deep trees. Alternatively, the iterative approach uses a while loop to handle the same two cases without recursion. While slightly more verbose, it avoids the risk of stack overflow and is often preferred for its robustness. Finally, if you were to ignore the parent pointer, you would need to start the traversal from the root node. While this is a valid approach, it's less efficient, with a worst-case time complexity of O(n), and it fails to leverage the unique advantage provided by the parent pointer. Each method has its place, but understanding their strengths and weaknesses is key to selecting the right one for a given problem. Great job! We've successfully solved Inorder successor in BST2. Remember, mastering tree-based problems builds a strong foundation in data structures. Thanks for watching, and be sure to stay connected for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!